My name is Peter Motivali. I'm a professor at the University of Missouri and chief instigator, I guess, of this CIRTL cast. This is the last CIRTL cast on this topic, which is innovative methods to integrate writing assignments in the STEM classroom. We've really saved, I think, the best for last. And this one is going to be addressing designing group-based writing assignments for problem-based learning courses. And it's really exciting because Andy Winholtz, he's an associate professor in the Department of Mechanical and Aerospace Engineering, has really been a pioneer here on the campus in the engineering program with other colleagues in developing this for his classes. And so he will be sharing his experience today. So Dr. Winholtz, please go ahead. Well, actually, I think we're going to talk with Kate first.
Thanks, Peter. And Andy, I'll turn things over to you in just a minute, or I should say Dr. Winholtz, my apologies. I'm Kate. I work with the CIRTL Network, and we are co-hosting this event series along with Peter Motivali at the University of Missouri, although he certainly is doing the brunt of the work. So thank you so much, Peter, for the wonderful series that you've put on this month. Before we get started, I just want to make sure that folks are familiar with CIRTL so that you know why we're here, and familiar with the software so that you feel comfortable engaging and interacting during today's event. Because first and foremost, we run these events for you all, for the folks in our audience, so that you can learn, so that you can take lessons learned from these events back into the classroom and use them to become stronger teachers, stronger learners. So with that said, welcome on behalf of CIRTL. CIRTL is the Center for the Integration of Research, Teaching, and Learning, and we are a network of 43 universities and colleges across the US and now into Canada, all working together to advance evidence-based STEM teaching and learning approaches to help make the sciences more diverse and more inclusive. And to that end, we run online events like this one. We have an online journal club and courses and workshops that we run, in addition to some other programming. And all of those are designed to help bring together people from across the country, from across the 43 institutions that make up our network, to learn together in dynamic and interactive and active environments like the one we're in today. So feel free to look up more about us on our website. And please do feel free to speak up and interact and discuss during today's event. I want to give you a few tips on how you can do that if you're new to this software, which is called Blackboard Collaborate. First and foremost, we love seeing people interact just by speaking up as you would in real life. If you have a comment or a question, don't be shy. Peter Motivali is in the room throughout the session today to help moderate, so he will grab any questions that you've got whenever they come up. You can, first and foremost, raise your hand if you have a question, and you can do that by going to the top of your participant panel and clicking this third icon over. That'll raise your hand, it'll let us know you want to speak, and then once you're called on, go ahead and turn on your talk and your video buttons to use your microphone and your webcam. Once you've shared your comment, go ahead and turn those off and click the raise hand button again to lower your hand. That way we don't hear any background noise, and that way there's room for other folks to turn on their equipment as well if they have additional comments or questions. Now, we don't require that you have a microphone or a webcam if you come to our events. Maybe you're on the go, maybe you're in a shared lab space or a shared office environment where you can't speak up. That's totally fine. Don't let that keep you from talking. We want to hear from you. We really, truly do. We've got a chat window in the room. That's super easy, super intuitive to use for many, many, many people. It's right down here. Use it as you would any other chat window. There are also going to be some specific moments throughout the event today where you'll be asked to write directly onto the slide that's in the room. And you can do that by looking for this vertical toolbar. You'll see it to the left of the slide, and selecting this fourth icon down. You want to click it and then click it again, 2 clicks, to get this icon with the A and lines next to it. That will let you create a text box directly onto the slide so that you can type your thoughts there. And that way it kind of becomes an online interactive discussion board type experience for everyone. So those are the tips I have on interacting. Please don't be shy. Please feel free to speak up. This event is for you. And it's the last event in this series, so it's your last chance to speak up. If you have questions, I'm in the room throughout the event, and I'll be keeping an eye on the chat window for any issues folks are encountering. So with that, I will hand things over to Dr. Winholtz.
Well, thank you, Kate, and thank you, Peter. I'll advance here. This is largely out of my engineering materials course, and the first picture here is students as I enjoyed seeing them. I kind of had hoped these tables would be the premier site and people would race to the table so they'd get the table so they could sit around in a circle and talk. But some groups would do that, many didn't. But that's kind of how I envision this should happen. This surprise over here surprised me in that these guys found an empty classroom and commandeered it and sat in the front row facing the whiteboard and wrote equations and talked about them. So I thought that was great. This picture here, parties aren't really so guilty, but it was the closest thing I had. And it was kind of the situation I didn't want to see that I saw a lot, which was one person sitting at a computer working and 4 people behind them watching them work. And that's kind of what you want to avoid. But that's how a lot of them worked. So one of the points I want to make is that you can start small with this and then build up to bigger problems. And this is something I did last week or so. And it was just making a small problem. And what I did was basically change my old lecture notes. So what I did for this presentation was grab my old lecture notes. And this was an example problem from that lecture notes. And just pretty much copied it directly here. So you want to carburize a gear. And here's some parameters. And then it asks a pretty simple question. What's the composition at a certain depth after 10 hours of carburizing? And here's the solution. You can do a little pattern matching, and you find in the equation in the book that we've given you everything except one variable. So you plug everything in except that variable, do your calculations, put your answer in a box, and that's one way to present things. And that takes about 5 minutes of lecture time. And I don't know that the retention is all that good. So here I've recast essentially the same thing in a different way. And I gave this as a quiz a week or so ago. And I'll just let you read it there. But it's largely the same problem. So this embeds it in a little more of a context, and a lot, the information isn't as clear. And the students are not prepared to tackle this problem yet, but one of the keys is to talk them through it. So I didn't actually do this time, but if I were to add a writing response, this is what I would do, is to make this a writing assignment, is have them write a letter and discuss what results they had and the implications of their calculations. I think on this one, I would actually tell them not to include the calculations as an inappropriate audience, but let's focus on what do the calculations mean. So what I'd invite you to do here is just, what do you see as the differences in the two approaches? So if you could write, as Kate suggested, on the screen, and just what do you notice about the differences in the two approaches? Well, I appreciate the Bloom's taxonomy response in that it's engaging them at a higher level, kind of getting beyond just simple calculation. That's one of the keys, I think, is in kind of engaging them deeper and not just doing calculations for the sake of doing calculations. Well, I kind of put some things down here. Lecture notes are very straightforward. It was a plug and chug problem. Every value in an equation was given except one. You do the algebra to isolate the one. This is what I find students are prepared to do. It's what they're used to, but they're not prepared for a kind of problem where things have missing information. You have to make assumptions. You had to make some approximations here. There's actually two parts of heat treatment. How do you handle the fact that there's two parts? This really takes some experience of approximating, assuming, and finding missing information. And that's what the students lack, is experience. And I try to tell them that's why we're doing this, is so that you gain some experience doing it. One trouble you encounter is that students aren't prepared for this. And so kind of the worst response you can get is that you're doing something wrong because I don't like this. You're not doing it the way everyone else does. So how does this work, or will it work? The lecture notes, I can do that in 5 or 10 minutes, and you can give a test where you just change the numbers and everyone is able to kind of do it. It is a story problem like that. It probably took me 40 minutes to get through that, to explain the calculations. This time it went really well in that the students were engaged in discussion of what kind of assumptions and approximations you would make. Scaffolding we're going to talk about, and for this particular problem, we did the in class, and so the scaffolding was just talking about assumptions, approximations, limitations, and where to find the missing information. Again, the problem is students often focus on the bottom line, and is this going to be on the test? Is all they want to know. I think the key is to engage them and get them talking somehow, get their interest in the problem. So problem-based learning is, we ran a full course in problem-based learning in the engineering materials course. Currently, I'm not running it that way, basically due to facilities. We're doing construction right now, and having a space for the students to meet isn't there. So the problem-based learning approach, though, we visited the med school. The med school is a complete problem-based learning curriculum, and they let us observe it for a while, so it got us interested in doing this. But the idea is that you present a rich context and ill-structured problem. Ill-structured meaning there's not necessarily a good right answer, where the answer is 0.8 and you put a box around it. It allows you to integrate theory and practice. The students learn by arriving at a solution. They have to dig in and try to solve it, and learn by going through the process. There's probably more than one correct solution, and you would characterize solutions rather than right and wrong as good and better, hopefully good and better. Note that in engineering, we have an accreditation body, ABET, which wants many of the things that a problem-based learning environment will provide. Open-ended problems where you may have to iterate solutions. You generate one, look at how you could improve it, and then go through a cycle again of improving your solution. They really like to see work in groups. They want graduates that have experience working with other people. And they always want communication skills. And they have to communicate with each other, and then they have to communicate their response to a problem. So advantages cited for problem-based learning is that it's active learning. They're doing more than passively receiving information, and it's integrated and holistic. It's got a context. There's a goal. We're going to see the goal here is to produce a written report that provides a solution. And the hope then is that this leads to deeper learning and hence better retention. That 6 months, a year, 5 years later, they've retained more information. And it represents the way learning occurs outside the classroom, so that we're trying to foster this lifelong learning idea and teach them to learn on their own. So groups work really well for this. You can give larger scope problems that are much more complex. They involve multiple tasks, so students have to work together to solve them. It's not as so practical for an individual to do it. They have to use multiple resources, not just the textbook. And so working together, I've seen kind of two ways that they can work, and they may go back and forth between it. One is to divide and conquer, where everyone is assigned a task. They go off and do it and then come back together. The other is to sit around the table and talk, work things together. And I don't micromanage how they do that. I'm happy to let them work however seems best. A written deliverable works well for this. It matches the complexity of the problem. They have to provide a context, explanation, limitations, caveats, all these messy things that make it a messy real-world problem lend themselves to a written deliverable. A presentation would also work very well, so a PowerPoint presentation by the group. I usually do a written report. Usually like to cast it so that their work, they come to a point where they have to make a decision or make a recommendation. So the goal isn't to calculate something. The goal is to make a decision or a recommendation. The calculations then support that. So I feel that they're being forced to function at this higher level. Someone mentioned Bloom's taxonomy, that it's this higher level. And so they're operating up at that higher level rather than just a simple calculation or memorizing things. Producing a report here rather than a number where you just put a box around it. So as a example, I'll give a problem that I would give the group 3 or 4 weeks to do this problem. The actual calculations can be done pretty quickly, but they have to go investigate, learn various concepts in order to solve the problem. So this would be a 3 or 4 week problem for a group of 5 to tackle. And so put them in a team, set it in the future, working for a company. I throw in a little astrophysics here that has nothing to do with the problem, but I just throw it in for fun. Make them learn what a Lagrangian point is in orbits. And then we're going to look at a small part of this spacecraft, design a pressure vessel. So here's sort of the guts of the problem. Pressurize the vessel. It's estimated it's going to need to last 8,000 cycles. And it's kind of a one-time trip. It has to last. You can't replace it if it doesn't. So you want to be able to prove it's going to work for the whole trip. So we have Judy Jetson suggest an overpressurization test. That you'll pressurize the test, and if it survives the pressurization test, your calculations should show that it will survive 8,000 cycles, maybe more than 8,000 if you're going to put some factor of safety in there. So I don't give them a lot of the details. They need to work that out. And then this is sort of the last paragraph of the assignment, is not a lot of information, just write a report. And this particular problem, you can change the numbers and you can get either a valid test or an invalid test by changing numbers. So I have done it both ways with this particular problem, change the numbers from one semester to another, and make it so that they get a valid test or they have to explain why it's not feasible. So let's try again. What, as you think about this, what things do you need to learn if you were in this position? What do you need to learn to be able to proceed? Throw you all into the student role.
As a reminder, folks can write directly onto this slide by going to the vertical toolbar to the left, selecting the fourth icon down, double-clicking it, and then creating a text box directly on the slide. If you have problems, you can go ahead and use the chat window.
So pressurization formula. So they, as a prerequisite to this course, they're supposed to have seen equations for stress in a pressure vessel, but most of them have forgotten that. That is something they do. Excuse me. That is something they generally know how to look up, that particular part. And this problem, as you might understand, is going to require some scaffolding. That's part that they mechanical engineering students should be able to get. The audience for the report, I usually tell them, is their peers. It's designed to be for other engineers. Oops. Well, just some advantages to this approach. The problem's embedded in a rich context. There's a lot going on here. It's not a 15-minute problem. There's a lot of messy things in there. But what it does is mirrors how practicing engineering work, and the new learning has an immediate application. So if you learn about crack growth, you can see how it applies immediately rather than, sort of abstract concept. One of the things I really like about it is that you can do larger, more realistic problems where you have to chain together several calculations rather than a problem being a little 15-minute thing. So I think it's a much more realistic to have larger problems where you have to bring multiple things together. Students learn to teach themselves and learn the process of solving problems. That all sounds good. There are disadvantages. Running the course this way, there's just not a systematic coverage of all the topics. So there's only so much time in the class. If we spend 3 or 4 weeks on this one problem, that means you just can't cover as much as you would in a lecture course. So the other issue is that some concepts just don't come up in problems that are realistic. Some of the background information, I have a hard time coming up with problems that deal with like fundamental crystal structure, defects in crystal structure that just don't come up in a good problem. Another disadvantage is that students just aren't accustomed to this style, so they are uncomfortable with it. They don't necessarily, and not everyone likes it, so some of them are unhappy about that. Also, a lecture hall just doesn't work. You can't tell people in this environment to get in groups of 5 and work together. This is the better environment. But to take this many people and spread them among tables is not easy. So I found the keys to making it work is scaffolding. You need to help them along. This is some of the scaffolding we use. I'll go through each of these items, but we start with lists of resources that they can learn from because they're unfamiliar with what's available. Give them some guiding questions to point the way. We do lecture on topics that give themselves to lecturing well, and then try to give lots of examples, particularly about writing reports. So first, scaffolding is some resources that they can use to solve the problem. So usually I point to relevant sections of the text. This is the text we use, and I'll tell them what sections of the text they want to look at in order to learn what they need to solve this problem. I also like to point to professional resources. For this problem, I point them to the ASM handbook, and this has got 20 to 30 volumes, so I'll point them to the particular volume they need. This one's on fatigue and fracture, and I in fact point them to an appendix in this volume that has cracks in pressure vessels and tells them how to deal with that. And it just would take a long, long time for them to uncover this resource on their own, so I point them to it. I point to web resources that I feel are trustworthy. Many of them work. Here's Paris law in Wikipedia. The reason they would have a hard time finding that is because they don't know that crack growth is governed by Paris law, because they have no idea who Paul Paris is. And so that's something that is an experience thing, and you can help them get pointed in the right direction. MatWeb is pretty easy to uncover, but I'll give them that. Some things are hard to find. In this particular problem, finding some of the material properties are hard. You have to pretty much go to the primary literature to find them. So for this particular problem, I actually give them the paper they need that will give them some of the values. One of the problems is students just don't know the terminology to go and do a Google search. So I find that true of myself in looking into a new area of research, is you just don't know what search terms to use. So that's been real key, is to help them get started with some resources. The next thing on list here, I've been calling a problem notebook. I'm looking for a better name for this. So if anyone has suggestions for a better name, I'm open to it. But I call it a problem notebook. And what I'm trying to get the idea across is that they should be doing calculations and putting their thoughts in a place like a problem notebook. Notebook is kind of how I did it as a student. I think the students are now using Google Docs. I try to point them to OneNote. This is where I've gone for my research notes, is OneNote. But what I do is give them a series of questions and proposed calculations that will help them get started. So answering these questions will help point them the direction they need to go. I'll withdraw the questions or the detail in the questions as the assignments go on. So for this particular problem, these were the problem notebook questions I gave them. This was late in the semester, so these are pretty terse. Earlier problems, all these questions would have been spelled out in much more detail. I probably would have given them example calculations and ask them to kind of reproduce them for another case. Another part of scaffolding is having classroom lectures. Some of the information is just most conveniently conveyed to the whole group of students with a lecture. So I like to assign the problem first, let them divide up tasks, get started reading, and then maybe on the second day start providing lectures. The advantage here is the students see the need for the material and can put it to use right away. I've kind of adopted the term just-in-time lecturing. But as an example, this is kind of thing that is be conveyed well in a lecture. Just it's a differential equation representing crack growth. They should be able to understand this, but getting through this math themselves for the first time is a little difficult. So taking them through an example, I think, is real helpful. Another key scaffolding thing is to walk among them as they're working and ask questions. Ask if they've made progress, if they're getting stuck. Sometimes they need a suggestion how to proceed. They won't come ask, but if you come by and ask them, they'll have some good questions for you. We really like to compare intermediate results. Ask you, is this the right track? Am I getting this right? One of the things I do, rather than just say, yeah, you got the right number, is ask them how they could prove to themselves they've got the right number. Can you calculate it another way and get the same result? They often need some help debugging computer code or spreadsheets as well. As far as producing their written output, they like to have some information on what do we need to write for a report. Often this is an early class among their engineering classes, and they don't have any experience with writing a big report. So I present a report to them, or a presentation on reports. I'm happy to make this available to anyone who would like it. Any of these scaffolding items I can make available to you if you send me an email, which has been put in the chat box, and I think Kate was going to copy it for me later, so that should appear again. But just giving a presentation on what you would like to see in the reports. And then I also give them an example report. And this is it started life as a student report, but I fixed some things and made it just how I wanted it, and changed the names to protect the innocent. And then I went through things that are common misunderstandings or troublesome issues, and put annotations. And so they have this example report that they can look to write their report. "20 years ago or so, our department put together a style book. That started as the advice for authors for the ASME journals. Those are the professional journals in mechanical engineering. We modified that and simplified it for student use, and we, as a department, want student writing to conform to our style book. I just reproduced the table of contents here. That is something, again, I can provide if you want to perhaps adapt something like that. But it kind of becomes the style guide for students in writing reports. Our campus writing program wants a writing intensive course to go have writing that is revised. So after receiving reports and making comments on them, I usually do another PowerPoint presentation that's comments on the reports, because you see the same things a lot. I do not change this report from semester to semester a great deal. It changes a little bit, but not a great deal, because they tend to make the same mistakes or need the same comments each time. So I don't have to change this a whole lot, but it lets me address a wide variety of problems that are frequent. The problems in the writing, usually the biggest issue is stating incorrect things, that they have misunderstanding or incomplete knowledge. They have logic flaws that make, I think, the biggest problem in their report. More of a writing issue, perhaps, is the converting their work, which is often very done well, but converting it to prose is a problem for the engineers. They'll have their calculations all done correctly. They can tell you it's right, but their argument in prose is not done real well. Another problem I see is that they don't incorporate as much in the way of graphical elements, tables, graphs, figures, diagrams, all kinds of graphical elements don't make it in there. And I really try to encourage them to do that, but I think they get close to the deadline and type out prose, and that's all that ends up in there. Many times the conclusions don't match what the introduction promises, so there's that mismatch. And I encourage them to look at their conclusions, go back and read the introduction and see if they complement each other. And then just correctly explaining their calculations is a frequent problem. And then there's the ongoing problem of just following conventions. In particular, group writing has its own problems. I think it's getting better, and I'm not sure the source of that. But in the past, the group writing on average was worse than individual writing, in that if you had 20 students and got 20 individual reports, the average would be better than 4 reports written by groups of 5. That the reports written as a group are actually worse on average than individual reports. And so there's a trick to learning to write as a group. The problems you see were that it was just obviously stapled together, that you can tell where one person wrote one section and then the next person wrote the next section. They just lack coherence. The same topics covered in multiple places. They switch terminology. They'll call something one part at the beginning of the report, and it's called something else later. They use degrees Fahrenheit in one section and then switch to degrees centigrade in another section. So my biggest advice to them in writing as a group is that somebody's got to go through and do a final edit. Lately, I've been seeing the group writing get a lot better, and I don't know if that's my interventions or that the students have learned to use some tools that really help them write better as a group. I think they just naturally use Google Docs and other things to collaborate, and I'm thinking they're really making good use of that, and they're getting better. The students are much better at me than finding ways to collaborate. I don't even text, so I don't know all the things they're doing. I do give them some advice on writing as a group, so I've got a presentation I give And as I said, the main thing I'm stressing in this presentation is that somebody has to take responsibility to do a final edit and kind of ameliorate all those issues. One of the things that you end up with then is that you need to evaluate individuals in a group written product. A couple ways that can be done is peer evaluation, or ask them to write you another item that reports who contributed to what. I'm still trying to learn how to do this well. I don't feel I've got a good handle on it yet. I tend to ask for a peer evaluation, and I always don't feel I get good peer evaluation. They just, everything is okay, or a group is not functioning well and one set of them doesn't like the other set, and it shows up in the peer evaluation. Something I've been toying with is asking them to write and explain who did each of these tasks. And one of the things I want to get out of this is to emphasize to the students that writing a report is much more than just putting words on paper. That a literature search, looking up parameters, creating an outline, going to the instructor to ask questions, creating the graphics, all of these things are part of writing, and it's not just providing the words. And if I ask them then to who contributed to each of these tasks, it will emphasize to them that all of this is part of generating a large report. So this is a bit of a work in progress, but I want to give them a list of these things and perhaps ask them to say who is going to do these tasks, and then evaluate afterwards. Downsides of the group work, one is facilities. It's not easy to do in a big lecture hall. We've done it in smaller groups by letting them kind of rearrange desks in a lecture hall if they're movable desks, but that can be a problem. It's nice to have a facility to work in, particularly like a computer lab or something where they can work in groups. Another probably the biggest problem is that students don't participate evenly. Someone always shirks their work, and somebody in the group is usually carrying the biggest load. This can lead to conflict. Haven't had a huge problem with conflict, but once in a while students will come ask you how to deal with other students in their group. Assigning students in groups can be done randomly or letting them self-select their groups. I've done both, and currently I let them self-select. I think that's a little unfair to students that haven't been there long or don't know other students very well, because they aren't able to get in a group of peers that they want to be with. Random helps that, but I think the self-select helps prevent the conflict perhaps a little more. But I don't have a good solution or good recommendation there. They both seem to work. The other aspect of group work is whether or not their schedules mesh outside of class. You can only give them so much of your class time, and they need to meet realistically outside of class, and it's hard to get them together to meet outside of class. So they probably need to judiciously meet together and then split up tasks to work on. Just some final conclusions that problem-based learning with a writing component, I would start small, something like the first assignment example I gave, and then work up to larger ones. Written documents are a good deliverable for complex problems. They're very authentic to the profession. Providing a written output for what you've done is going to be authentic. And it forces facing the complexity and subtlety in a problem. You have to explain things, talk about assumptions, and it just provides a very good complement to a complex problem. So group work has benefits of learning to tackle these more complex problems that are higher in learning level, and they also learn from their peers, which I think is going to have some long-term benefits. So I will stop there. Thank you all. Does anyone have questions?
Andy, I had a question. How do you avoid the students doing everything at the last minute? Do you also scaffold in terms of having bits of the assignment due at different times?
That would be the strategy. I'm not good at being that organized. When they are meeting in class, I can run around and check and make sure they're on track. It's harder when they're doing the group work outside of class, and that does become the problem, is that they do it at the last minute, like we all do. I think you're right that making subparts due at different times is the solution to that. That requires organized teacher, which I'm not the best at. Other questions?
As folks think through questions they might have, I definitely want to encourage you all to take this brief survey that we have linked to on this slide. The survey is totally anonymous, and even though this is the final CIRTL cast we're running this year, your feedback here helps inform all of the programming that we do in terms of what's useful to you and what's not. So we really do take this feedback to heart. As I mentioned, it's totally anonymous, so if you can just take 1 or 2 minutes to fill out the survey, that would be hugely helpful. And again, if you've got any questions for Dr. Winholtz, we've got a few more minutes before the hour is up.
Andy, there was something in the chat room earlier on from Dennison about how does your syllabus look like? You have lectures on writing and group work and different assignments. How is it all organized?
It depends. We've run a complete problem-based learning course where the course just consists of a series of problems, 4 or 5 problems through the semester. And so the syllabus is some problems. We go ahead and have exams anyway. We kind of had to learn that you got to be judicious with the exams, because they need to, exam questions need to be over the problems and what they should learn in the problems, and not over what you would do in a lecture. So I included exams in the course just to evaluate what they're learning. If you're not careful, it can kind of run into 2 parallel courses, one where they cram for exams and the other where they do the problems, and those 2 don't interact enough. So you need to be careful to make sure the exams reflect the problems. I'll put my email in the chat box again. I'm happy to share any of the presentations or other scaffolding items that I've got. I'm happy to share that with anyone who would like to see it. Might spur your thinking.
I hate to be asking questions, but one of the things that I've noticed in the other presentations is that in many of the courses they have a sequence. Rainier Glazer had a sequence where things were sort of followed each other. I have one where I go from informal to formal. Is that going on too in your course?
Well, a couple of things go on. One is that the problem notebook where we ask questions starts very detailed. The first problem we would do would be incredible detail in the problem notebook. So like complete tables of calculations already done, and then they just have to change some numbers and repeat them. Just a lot of information to help them get through the first time. And then the sequencing is to withdraw that detail that you give them to get through it so that by the end they're able to tackle new problems on their own better. Although there's parts of the scaffolding you're always giving them, like resources. The other is that it attempts to go through problems that deal with material in kind of a progressive way that would follow a textbook. So a simple problem at first that's dealing with the simpler concepts, and then move on to later problems that deal with concepts that would be later in a textbook. The disadvantage of this approach is that there's holes, there's things that do not get covered. So I would say the day after the final exam, somebody having a traditional lecture course is going to have a fuller mind full of materials. But you know, the hope with the problem-based learning approach is that 6 months, a year, 5 years later, they're going to remember all this much better than someone who crammed for exams the night before and got through that way. There's a question that's how big are these classes? I have run this course in engineering materials up to 90 students, but I had a co-teacher and TAs to help. But it gets a little unwieldy with that many students. A good number is 20 to 40. But we have done it with large groups, but you just need the room to spread out. The longitudinal data would be great. We have a record of who has taken these classes. I'm not sure how we're going to get them to take a materials exam in their spare time. But some sort of survey like that would be a great thing to try.
Andy, I want to thank you and all the participants for being involved in this series. And as I understand it, these videos will be available for those of you who weren't able to attend the previous sessions. And we're all appreciative of the sharing of all of this combined experiences. And I think for many of us, we're going to try and utilize these and hopefully work from there and develop our own approaches. And I encourage everyone to contact the speakers. Many of them also have provided references that you might want to utilize. So thank you all, and thank you for Kate and Miranda for coordinating this in a very nice way, and we appreciate it.